So now we are ready to hear Bohdan Feshchenko's speech about normal forms of Morse-Bott functions without saddles on compact-oriented surfaces. So Bohdan, are you ready to start?
Yes. So we start with needed definitions. We consider smooth compact surface, and by P we denote a line or a cycle, and we will consider the action of the group of diffeomorphisms of M, Pm on the space of smooth p-valued functions by the following rule. We take a function f from here, diffeomorphism h from here, and the result of this action is the following composition h and f. And for a smooth function f, we consider the following two spaces. The first one is the stabilizer of this smooth function, and the orbit of this function f with respect to the action c. And we denote by SID f a connected component of stabilizer containing the identity map, and by OFF a connected component of the orbit containing f. And we consider the following class of smooth function. So the smooth function f on M belongs to the class f if the following condition holds. So the first one, our function is locally constant on the boundary of M. The second one, a set of critical points, sigma f, is a disjoint union smooth submanifolds of M, and it belongs to the interior of M. And the last one, for each connected component C of this critical set, and each critical point P and C, a local representation Fp with respect to some charts near P and near Fp of F is either a homogeneous polynomial Fp without multiple factors. For example, this one, or this local representation is given by this formula for some constant and C depending on C. In case A, critical point P is an isolated critical point, and in the case B, the point this point is not isolated, and C is a critical cycle. And in this picture, you see the regular neighborhoods of critical cycle, or on oriented surface when N is even and NT is odd. And a critical cycle C is extremal if this number is even and non-extremal otherwise. The following inclusion codes. So this class F contains the class of Morse-Bott functions, which is locally constant on the boundary, as well as the class of Morse functions locally constant on the boundary. For functions from this class with the only isolated singularities, the homotopy properties of these spaces are known or well studied. And for arbitrary function from this class, the following results hold. So for any function from F, the connected component of the stabilizer is either contractible or has a homotopy type of a cycle. And to be more precise, the stabilizer is contractible if F has at least one saddle point or a degenerate isolated extreme, or M is non-variant. And the stabilizer is homotopy equivalent to a cycle otherwise. So for almost all functions from this class, the stabilizer is contractible. And it is interesting to characterize functions from this class whose stabilizer is homotopy equivalent to a cycle. And we consider the following subclass F0 of this class of smooth functions whose isolated critical points are non-degenerate local extremes. And so, due to this result, for all functions from this class, the stabilizer is homotopy equivalent to a cycle. And the following theorem holds true. So if you have a function from this class, 0, then the following condition holds true. So Eulerian characteristic is non-negative. So M is diffeomorphic to one of the following for surfaces: a cylinder, a disk, a sphere, or a torus. The function F has this number of Morse local extremes. The function F can have any finite number of critical cycles if M is not diffeomorphic to a torus, and if M is diffeomorphic to a torus, then F has only even number of external cycles. In particular, if F is null homotopy, then it has at least two such cycles. And it is easy to see that this concrete form function belongs to this class. So this is the concrete formula, the simplest functions from this class. So it is the standard cylinder, and F is a height function, a disk. F is a sum of squares, a sphere, a unique sphere. The F0 is a height function and a torus, and F0 is given by the angular projection. This function at 0 has no critical cycles, and we call it a prime function on n0. The simplest one. And the following theorem is our main result. So any function from this class F0 admits the following decomposition of this form for some diffeomorphism where F0 is a prime function and a function kappa satisfies the following conditions. The first one, the kappa has the only finite number of critical points in which it is not flat. And the second one, the kappa doesn't have critical points at this set. This factorization one we will call a normal form, and it is not unique and depends on the choice of H. Thank you very much.
Okay, thank you very much, Bogdan. It was a very interesting speech. So